All right, so we are almost done talking about the different applications of the classical gravitational two-body problem. The last example that we'll talk about here is this so-called gravitational slingshot effect, sometimes called the swing-by mechanism or gravity assist maneuver for spacecraft. And it's sort of a stealth bridge to the three-body problem, because this effect really does depend on having a third body there to set the scale of the motion of the other two. But we'll get to that. Earlier we talked about changing your speed in a rocket by some delta V of velocity by burning your rocket engines. But there is another way to do it if you don't have enough fuel. This will involve orienting yourself into a hyperbolic type orbit, a hyperbolic flyby between the spacecraft and some massive object. I just wanted to sort of refamiliarize you with the different shapes of these hyperbola, right? There's the small angle collisions, right? Small angle deflections, and then there's much larger angle deflections, and those angles are sort of inversely correlated with the eccentricity of the hyperbola. So again, what I've plotted here with the little origin at the dot in the center at the focus, it represents the path taken by the relative position vector and relative velocity vector as it swings by. And of course, when you bring up this relative velocity, you remember the key fact that we made use of when we talked about Coulomb collisions, the fact that the relative velocity on the ingress, long before the actual collision happens, and the relative velocity on the egress, initial and final, are equal to one another. I'm saying that's true in the center of mass frame. Actually, I guess the definitions of the relative velocities are, this thing is true in any frame. But yeah, so we've been doing a lot of our thinking so far in the center of mass frame for the two-body problem. But we need to transform back into this inertial frame, because the two-body problem that this spacecraft will encounter with some planet is just a temporary thing. The spacecraft has a job to do to get from one place in the solar system to another, and that's all defined by some larger inertial frame. But yeah, for the two-body collision, we can talk about M1 being the spacecraft, M2 being the planet. So M2 is much larger. That means that the velocity of the center of mass frame is dominated by the heavier thing. We've talked about this weighted average before, and that's pretty much just the velocity of the planet itself. And now this V2, this velocity of the planet itself in the inertial frame, we have to think about, because, right, the planet is in orbit around the star. The star, or the sun, is this stealth third body that sets the scale, because we can consider the planet's motion to be some known orbital velocity, right? That's something that we're saying, that we're sort of setting as the scale of this system. Right, so if that's known, that means that we can, when we want to transform the spacecraft's velocity, V1, into this center of mass frame to look at these relative velocity vectors from the solutions to the two-body problem, V1 minus V2 is pretty much V1 minus the center of mass velocity, right? So the relative velocity is pretty much the velocity of the spacecraft in the center of mass frame. So let's sort of set up a problem where we have a low eccentricity or large angle collision type hyperbolic orbit. Now, the cartoon I drew at the bottom shows the ingress and the ingress sort of being anti-parallel with one another. You'll never get that exactly with a hyperbola, but for values of the eccentricity getting arbitrarily close to 1, the angle between those two ingress and egress becomes, that they become much more parallel to one another. So just looking at the x component, or the component along that sort of parallel direction, is the approximation we're making here, and the real result is not too different. Okay, so let's actually try to write down the velocities in these different coordinate systems. We'll eventually make use of the relative initial and final velocities, speeds being the same. But let's start by assuming the planet is moving in the plus x direction, and thus the center of mass of this collision is also, or this interaction is moving in the plus x direction with capital V. The initial velocity of the spacecraft is in the minus x direction, so we can sort of set it up just as some minus constant s, where s is a positive constant, along the x axis. So that's the V1 of the spacecraft in the inertial frame on the ingress. So now when we want to talk about the interaction, we need to transform from the inertial to the relative center of mass coordinates. So the relative speed between the planet and the spacecraft is just as we set up here, V1 minus the center of mass velocity. And that now, because they're approaching one another, the magnitude is going to be bigger, right? So it's minus s minus v, where both s and v are positive numbers. So that's the initial velocity, the initial relative velocity between the spacecraft and the planet. Now we can make use of our initial equals final. And in the way I've drawn the cartoon, the actual vectors are oppositely directed, but their magnitudes are the same. So the v final can now just be given by minus v initial. And again, this v is the relative. So it's just s plus v, positive quantity. It's pointing to the right over here. And right, so we have that. And now we can go from the relative coordinates back to the inertial frame coordinates, just using that same transformation that we had on the previous slide, but solved now for v1 in terms of the v. And, well, it's now s plus 2v in the positive direction. So when you actually compare the magnitudes of the velocity of the spacecraft in the inertial frame from the before to the after, the actual magnitude of the velocity, the speed has increased from s to s plus 2v. So the spacecraft has gotten a boost. It's gotten a gravity assist, and it's been sped up after this slingshot maneuver. Yeah, there's different ways we can think about this. There's a whole bunch of different analogies. I've got a sort of a summary of them here, right? In the upper left, there's this sort of straightforward analogy of throwing a bouncy ball at an oncoming train, and the ball bounces back with a larger velocity. You can think of this as a classical collision problem where momentum is conserved, energy, kinetic energy is conserved if it's an elastic collision. And it is true that if you throw a bouncy ball at an oncoming train and it bounces back, it does actually rob the train of a little bit of its momentum. You do actually slow the train down by throwing something at it, but because the mass of it and its momentum is so large, you're really not slowing it down by that much, but the transfer of momentum from one object to the other, to the ball, actually can provide a huge change in its momentum and kinetic energy. Right. That's exactly what we're talking about here with the spacecraft and the planet. In the lower left, there's this ball drop experiment. If you've ever taught or TA'd an intro class that talked about core collapse supernovas, a stars and galaxies type class, you might have seen this demo, because it's a similar type of thing. The larger momentum of the basketball at the bottom is transferring its momentum to the little golf ball. And even though you're dropping it from just a few feet, the golf ball can be accelerated up, 30, 40 feet in the air by this thing. And it's a very similar thing to the core collapse shock mechanism from the neutron star that's growing at the center of a supernova. In the upper right, there's this other analogous situation that you often see in plasma physics courses, this phenomenon of Fermi acceleration. You can actually accelerate a small fraction of the particles in a plasma to very, very high energies if it's in the vicinity of an MHD shock, because the velocities, in the frame of the shock, it's almost like there's a converging flow, like the particle in the oncoming train, which can provide this acceleration. Yeah, I looked around for other types of demos where you sort of have two converging plates, like in the trash compactor down there, and a ball bouncing between them. I think you could create a nice demo where maybe if you don't have gravity, do it side to side, and you look at the period of the bouncing of the ball, and it actually speeds up quite a bit as the as the plates converge, and you could see this transfer of momentum to the particle. But yeah, I couldn't find anything that actually illustrated that. This is sort of a universal process, and you can make use of it to speed up your spacecraft or slow it down too. You can do a reverse gravity assist. This is the last topic. You know, if you approach the planet in the same direction along which the planet is moving, and then you swing around it in the other direction, that will slow down the spacecraft. And there's a very nice example of this. This is what Parker Solar Probe is doing to get closer to the sun. It's got to slow down to shed the angular momentum that it had by virtue of the fact that it was launched on Earth. You know, large orbit means larger angular momentum, so it's got to get rid of it. And these encounters with Venus, it's going to have many of them, are one way to do that, right? You see the trajectory of the orbits. You can sort of see where it starts out on Earth down here in 2018 when it was launched. And you can see that it's going in this counterclockwise direction, and that's also the same direction as the orbits of the planets. So whenever it approaches Venus, it's approaching it along the orbit, and it slows down each time, and each new elliptical orbit has a perihelion closer and closer to the sun. I was kind of surprised. Last week there was a Parker Solar Probe Science Working Group meeting, and there was a presentation on the latest Venus encounter this past July, and I was kind of surprised to see this plot, to see that the spacecraft actually approached the surface of Venus at a closest approach distance of only about 1,600 kilometers. You know, the Venus has an orbit similar, has a radius similar to the Earth, 6,000 kilometers. So it really sort of grazed through the outer atmosphere or ionosphere of Venus. So yeah, this solar mission is going to actually teach us some things about about Venus's atmosphere as well. All right, I guess that is all I had about gravity assist maneuvers, and we will soon move on to the full three-body problem in earnest.